Right, guys, roll up your sleeves and pull up your socks. Not because we're going to talk about Dr. Doom, but we'll do a quick review of AP Physics 1 for the new exam pattern. Let's get started. And yes, guys, this includes fluid mechanics as well. Unit 1, kinematics. What is kinematics? Kinematics is all about distance, displacement, velocity, acceleration, speed, and so on. We always start by talking about vector quantities. So these guys are vector quantities. What are vectors? Having magnitude and a direction and a specific direction. So what are their counter scalar parties? So distance is a scalar, speed is a scalar, acceleration doesn't really have a scalar counterpart. These are all scalar people, so they don't have a direction, only magnitude. Quick question for you. What is pressure? No, pressure is, we will feel like pressure has a direction, but no, pressure is a scalar quantity. Heads up. All right, then we talk about equations of motion. Remember, equations of motion are only applicable when the acceleration is constant. Honestly, you don't need to worry about that because when acceleration is not constant, it is a part of physics C mechanics, which you guys are not taking. So for physics 1, acceleration will be constant. And if it is constant, you're very familiar with these three equations. There is another equation that doesn't involve the acceleration. It is given by delta x is equal to v final plus v initial over 2 multiplied with time, where delta x is again the displacement. So v final and v initial are just a v and u that I've represented over here. So that doesn't involve acceleration and just takes the average speed into account, right? Okay, the graphs are very important. Slope of x versus t is velocity. Whenever you, what is x, guys? X is the displacement, and what is t is of course the time. Whenever I have a whenever I find a slope here, it gives me a velocity. Let's say, for example, the curve is like this. So at this point, the slope is 0, so it is at rest momentarily. At this point, the curve has a positive slope, so v is positive. At this point, the curve has a negative slope, so v is negative. What is the meaning of v being positive? It is conventionally going to the right. This is at rest. This is conventionally going to the left, right? As in not the right direction, just the right, whether you understand or not. Okay, V versus T graph. V versus T graph, the slope is acceleration. This is one of the most important graphs in all these because it gives us two attributes, V versus T. As you can see here, area under V versus T also gives displacement. Remember, this area is a sign sensitive. Okay, I will talk about both now. Let's say I have a graph that looks something like, that's a gross one, that looks something like, it's a gross one as well, that looks something like this. So if I want to talk about the area between T1 and T2, if I say this area is A1 and this entire area is A2, then I will not really add both the numbers, I will rather subtract, because it is sign sensitive. Below the x-axis is a negative area, so this is the total displacement. However, if they are interested in acceleration, I'll just find the slope at any particular point. Over here, for example, it has a positive acceleration. Over here, for example, it has a negative acceleration. Over here, for example, it has a 0 acceleration. So this is how we can do all this. Next is projectile motion. Remember, projectile x and y both are changing simultaneously. You have to resolve components. You have to treat x and y components separately. If this is v naught that is thrown at some angle, you have to make sure that you divide it in v naught cos theta and v naught sin theta so that you analyze vertical and horizontal components separately. Some very important things that you have to notice here. At maximum height, there's a misconception that entire speed is 0. No, entire speed is not 0 because this guy is never changing because we don't have any air resistance, no acceleration in the horizontal sense as we have written over here. So Vy only will become 0. Vx will still be V naught cos theta. At the top, there is also a misconception that the acceleration becomes 0. No, acceleration is not 0. It is pointing g. It is g pointing downwards. That's what is happening at the top. A couple of other formulas that you should be aware of, although these are only if you have time and if you don't know these. The range, so I'm talking about the projectile that starts and lands at the same position, and this is V naught, this is theta. I'm going to give you formulas for three attributes. One is the maximum height, one is the range, and one is the time of flight. time of flight. The time of flight is given by 2 v naught sine theta over g. The maximum height is given by v naught square sine square theta over 2g. The range is given by v naught square sine 2 theta over g. Related to this, we have two very interesting scenarios. The first scenario is if I have a situation where from here, if I throw a ball at different angles, let's say V like this, or V like this, or V like this is all the same. These are all of the same height, although they may not look like, but these are all of the same height. They will ask you, compare the time taken in all the three situations, compare the speed taken in all the three situations. Time, I'm going to talk about that later, but for the speed, it's going to be same. It's going to be same. This is not going to change. The speed will not really change at the a time when it hits the ground. The reason is in energy conservation, which we'll talk about later, but yes, this is important. Another interesting thing is about a projectile, the regular projectile motion. Let's say I have three projectiles fired like this, but all of them reach the same maximum height. Something like this, and this also goes like this, although but the maximum height is same for all of them. And they will ask you compare the time of flight. Remember that the time of flight is going to be same for all of them, because time of flight only depends on the vertical vertical component as in the height, which is same, so it's going to be same for all of them. Next, we're going to talk about force. Force is all about vectors. Force as an SI unit of Newton. And the most popular second law that helps us to solve the question says that F net is equal to ma. Forces cause acceleration, of course, that's what we have. Now, in order to find any situation that involves in Newton's law or dynamics, you have to draw FBD. Free body diagram is extremely important. The common forces that we use in FBD are gravity always acting downwards, normal perpendicular to the surface, tension always pointing away from the object, and then we have a friction, which is mu times a normal reaction depending on the situation. I'm going to quickly draw some situations here. There's some popular free body diagrams here. Whenever you have a situation like this, tensile X opposite and mg is down. Mg is down, doesn't matter where you see. But over here, Fn is obviously perpendicular. But here on an inclined plane, you have to be careful that Fn is perpendicular to the surface, and mg is to be resolved as mg sine theta and mg cos theta, where theta is the angle with the surface. And on the block, on the top of a block, this is an interesting one. All these were frictionless, but here we have a friction. If I'm going to pull the F with F external slowly, then this block will also come towards me because there is a friction between these two. An equal and opposite friction will act on the big block as well. Now I want to talk about elevator. So the apparent weight in an elevator on a bathroom scale depends on where there's the acceleration. Remember, acceleration, not the velocity. If it is accelerating up, then it will be over weight. If the acceleration is 0, it will be same weight. But if the acceleration is downwards, it will be under weight. Right, next is what is in equilibrium? Equilibrium means the net force is 0, and if the net force is 0, then the acceleration is 0. Equilibrium doesn't mean that the force is 0. No, F net is 0. F net is equal to 0 means that maybe an object is being pulled by 10 Newton to the right and 10 Newton to the left. So yes, net force is 0, although there are individual forces. Hooke's law. Hooke's law is for an ideal spring, the force by an ideal spring is given by negative kx. Why negative? Because this is restoring in nature. Remember that x is not from the equilibrium. X is the amount of stretch or compress that is from the spring's natural length. This is what you have to remember. Next is circular motion. In the circular motion, remember, Fc is not really an extra force. Fc is just the net force acting towards the center, which is given by mv square over r, and the acceleration is v square over r. Related to this, there are two conditions: banked and unbanked curve. In unbanked curve, there is no incline, and the friction provides the necessary centripetal force. While in banked curve where there's an incline, the normal reaction also contributes. The component of the normal reaction also contributes towards providing the centripetal acceleration. That's a very interesting thing about banked. That's why in a banked curve, higher speed is possible without slipping, because still one for some speed normal can handle, and then friction also assists. But in unbanked, no, there is no contribution of friction. Next is gravitation. A gravitational force is all about attractive between any two objects having mass. Remember that if you are given spheres, they can easily trick you by giving you some distance between their surface. But no, the distance r that we take in this formula, gm1 m2 over r square, it is center to center. So in this case, you are going to take r1 plus l plus r2. Okay, that's first. Always attractive. I already talked about this. Next, a very important formula is what is the gravity due to a planet outside at a distance r. Once again, I'm taking the distance r from the center, not from the surface. And the formula for the gravity is gm over r square. Once again, another pitfall is students usually consider that this m is the mass of an object that is placed here. No, this m is the mass of the planet that is sitting right here, because of which we are trying to find the gravity at that point. That's all about Unit 2. Unit 3, work, energy, power. All these three are scalar. Work, joules, SI unit. Energy, joules, SI unit. Power, watts, SI unit. Work is given by Fd cos theta. If it is positive, if the force aids the motion, which makes sense, because if there is an object and I'm pulling like this, obviously it is displacing somewhere here. So I'm doing a positive work on this object. Energy type, there are three energy types that we are supposed to understand. One is kinetic energy, half mv square, always positive, it can never be negative. The next is spring potential energy, which is half kx square. Remember, x is again the stretch or compress from the natural length. And potential energy, which is mgh. Now this can be positive or negative because it depends on h is h with respect to the reference, because this is all about reference. Next is about the types of forces. This is very important. Conservative and non-conservative. Conservative forces are only handful: gravity and a spring. There is another force, but that is for AP Physics C, E, and M. I won't talk about that. Gravity and a spring. These are conservative, which means that it will only depend on the initial and final positions and not the path taken. If we are doing a work in a loop, that it starts from a point and comes back at the same point, no work will be done, and the mechanical energy will be conserved whenever we only have conservative forces. On the other hand, the non-conservative, it depends on the path taken, non-zero in a loop, and any other force that you can think of: friction, air resistance, tension, normal, drag, etc. Anything that is non-conservative in nature. And here mechanical energy is not conserved because it is usually lost in the form of heat and sound, etc. Like I said, if there is no non-conservative force, the mechanical energy is conserved. When I say Ke plus Pe, I mean to say Ke plus GPe plus SPE, where GPE is the gravitational potential energy and SPE is the spring potential energy. That is always constant between two positions. On the other hand, if there is a non-conservative force, then the only change in this entire thing that we do is WNC, work done by a non-conservative force, plus initial kinetic, plus initial gravitational, plus da 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 will be equal to the final positions. That's how we conserve the energy when we have a non-conservative work. And remember, if the non-conservative work comes out as negative, it means that is lost in the form of heat. So sometimes they can ask you what is the heat lost by the friction. So they are basically asking the work done by the non-conservative force. Work energy theorem, really important, guys. The net work done by all the forces acting on a particular system is basically equal to the change in kinetic energy. The last thing is power. The power is work over time, or FV cos theta. What is F? Force. What is V? Velocity. And theta is the angle between the velocity and the force. Uh, these things will give average if these things are obviously constant, but it will give you instantaneous if these things vary. Then at any particular instant when we take, then it will give those values at that instant. Right, we are through with this unit as well. The next unit is linear momentum, easiest of all the units. Momentum, it's a vector quantity. The SI unit is given by kilogram meter per second, represented by P, and the formula is mass times velocity. The direction is same as the direction of the velocity. More important than momentum is the word impulse, usually represented by J as well. It is given by F average times time, or F average is given by delta P over delta T. This is a really important formula. What is delta T, by the way? That is basically the contact time, the time for which, let's say, the rubber ball hits a floor and then comes back. Then the time for which the rubber ball was in contact with the floor, that is given by delta T. Force versus time, if you're given a graph, then the sign sensitive area, for example, if the force versus time graph looks like this, and if you have an area over here as A1 and if this is A2, then A1 minus A2 is going to be the impulse in this situation. Next is law of conservation of momentum. If the net external force on a system is zero, then the total momentum is conserved. This is very important. What can be some cases for this? These are some popular cases that you can see. Cannonball question, collision of balls, gun bullet, astronaut wrench, throwing a wrench, and boy box, a boat river, as in a boy throwing a box standing on a boat in a river. That's also all the conservation of linear momentums. Next is types of collision. There is elastic, inelastic, and perfectly inelastic. If it's elastic, momentum, kinetic energy, both are conserved, but the objects don't stick together. Inelastic means only momentum is conserved, kinetic energy is not conserved, and objects do not stick together. Perfectly elastic, only momentum is still conserved, but this is the only situation, perhaps the easiest, where objects stick together. Kinetic energy is still not conserved. All right, this unit is done. Next one. Torque, arguably one of the most difficult units because it covers a lot of the things. Torque, vector quantity, SI unit, Newton meter. The torque is given by Rf sine theta, where R is the distance of the point where the force is acting uh, to the pivot. Pivot is basically the point about which we have a rotational tendency, and theta is the angle between R and F. Also, just like F is equal to ma, torque is I alpha, where I is the moment of inertia. Moment of inertia, basically a rotational mass, depends on the mass and distribution. There are already a couple of formulas out there for regular shapes, but for a point mass, the moment of inertia is given by mr square. Just like linear motion and rotational motion as well, if alpha is constant, then these equations are equally applicable, which can be easily, we can easily draw an analogy. For example, the first equation in linear world was v is equal to v naught plus at. So likewise, it is omega final is equal to omega initial or omega naught plus alpha t, and so on. Pure rolling is a very important word in the rolling motion. So if there is a rolling without slipping, also called a pure rolling motion, then the V center of mass is always equal to omega r. Likewise acceleration, tangential acceleration is always also equal to alpha r. These are very important terminologies. Also, in case of pure rolling, friction does not do any work. The work done by the friction is always zero because it's static. There is no slipping of that point. Right, done with this unit. Next one. Energy now. Energy and of the rotational kinetic energy is given by half I omega square, just like we have half mv square. M and I are equivalent, and V and omega are also equivalent. Total energy in case of a rotational motion, remember there are three energies involved. Rolling motion, because rolling motion is also going forward, is also rotating, and it can also change the height as well, right? So you have to make sure that you take all the three energies into consideration, and that's how the mechanical energy is considered. Angular momentum is given by I omega, just like a linear momentum is mv. M is same as I, V is same as omega, so the angular momentum is I omega. More important than angular momentum is the conservation of angular momentum if the net torque is zero. So for example, a very popular case is when two disks are rotating and the disk one is slowly lowered and kept on disk 2, and after some time they start rotating with the same omega. Find the net omega or the final omega. So this is also where we need to conserve the angular momentum, because the net torque effectively between 1 and 2 is cancelled and it is 0. Right, Kepler's law. Now, there are three laws of Kepler. One says that the law of ellipse, which means that the planets revolve around the sun in elliptical orbit, and the sun is at one of the focus. There are two focus of ellipse, but sun is at one of the focus, and the planets move around an elliptical orbit. More important than this is the law 2, which says that an equal interval the planets cover or sweep equal area. So let's say, for example, from here to here, it took 10 hours. And from here to here, it also took 10 hours. So this area that the planet has swept about the sun, that is going to be same. This also leads to another formula for conservation of angular momentum, which says that m1 v1 r1 is equal to m2 v2 r2, where m is not changing for the planet. So v1 r1 and v2 r2 are always equal, where r is the distance of that planet from the sun. In this case, we have considered circular orbits, remember. And the third law says that the time square, t square, where period square is proportional to the r cube for the planets, where r is the average orbital radius, also sometimes called semi-major axis of the ellipse. Right. Again, about the work done by the torque, that's also similar to, for example, work done by the linear world is RF sine theta or FR sine theta. The only differences here is just F is torque and theta, R is theta, and that's it. You multiply both, you will get the work. Remember that theta has to be in radians. The next is about the orbital speed and the escape velocity of the satellite. The orbital speed of the satellite is given by root gm over r, and you multiply a 2 here inside the root and it becomes the escape speed. However, remember that this m is not the mass of the satellite, it is the mass of the planet. R is not the distance from the surface, R is the distance from the center of the planet, remember. So these things are pitfalls where you have to make sure you don't make a mistake. What is escape speed, by the way? It's the minimum speed that we have to give from the surface that the object reaches infinity and also stops over there. And lastly, what is the gravitational potential energy between two objects? For example, a satellite rotating around a planet. It will be negative. That's negative is really important. Negative g, mass of the planet, mass of the satellite divided by r, where once again, the r is the distance from center to center of the planet as well as the satellite. Right, the next unit, unit 7, oscillations. Oscillations, SHM is always when the force is restoring in nature and is proportional to the displacement. That's when we call it as SHM. The general equation for the motion of the SHM is given by A cos omega t plus phi, but it's very unlikely that they will complicate this thing. There are only 4 standard positions where the SHM can start. If it can start from equilibrium going to the right, equilibrium to the left, right extrema obviously going to the left, or left extrema going to the right. Equilibrium going to the right will be a sine omega t. This will be minus a sine omega t. This will be a cos omega t, and this will be minus a cos omega t. The two popular systems that we have are spring mass, doesn't matter whether that's a horizontal or vertical. The time period is 2 pi root m over k, and omega is root k over m. There's another thing called frequency that we do, which is just a reciprocal of time period. The other system that we have is pendulum, which is given by 2 pi root L over G. Remember that the pendulum can perform SHM only when the angle is between negative 15 to 15 degrees, which we consider as small angles. It is worth noticing that doesn't matter which arrangement we are talking about, the maximum acceleration always occur at extreme positions, and its formula is a omega square, where a is the amplitude and omega you know, and the maximum velocity occurs at equilibrium with the formula a omega. In case of spring mass system, the total energy is always half Ka square. Worth noticing that it is not dependent on mass. This is applicable for whether we are talking about vertical or horizontal spring mass system. And remember that A is the amplitude from the equilibrium position, not from the unstretched length. This is the mistake that students do. So please be careful. Right, we are done with this unit. Last one is fluid mechanics. Remember, all the formulas that we are talking about will be based on consideration that fluids are ideal. That is, they are incompressible and they have zero viscosity. And yes, in AP Physics 1, they will only test you on ideal spring. Density is given by mass over volume. It's a very basic formula. Pressure is force per unit area. And for a pressure exerted by the fluid, by the way, fluid means air and liquid both, not just liquid. Uh, the pressure due to a fluid is given by rho gh, where h is the height at which we are trying to find the pressure. Let's say this is a beaker having a liquid, and if we are trying to find the pressure at this point, then this is the height that we consider. Remember, this is sometimes also called gauge pressure as well. Right, a couple of theorems important for us. Pascal's principle. Now, pressure applied is transmitted equally. Where will you see an application? Mostly in hydraulic case, where you will see this area as A1, this area as A2, and here you will have a mass, and here you will have another mass, and you will say that since the pressure is same, so you will equate basically the force over area. You will say F1 over A1 is equal to F2 over A2. This is a very widely used principle of Pascal. Next, buoyant force, very popular. Buoyant is basically the weight, the force exerted by the liquid in the upward sense, and its value is given by dense mass, volume of the fluid displaced, or the liquid displaced, times the is given by mass of the fluid displaced times t. And the mass of the fluid displaced is the volume of the fluid displaced times the density of the fluid, and sometimes volume of the displaced fluid, if the object is completely submerged, can also be replaced by volume of the object. So sometimes this formula is also used. Now, there can be two cases. Either object can float or the object can submerge. When I say float, I mean to say that, let's say here we have a liquid and here we have a stone here, which is floating, right? And then the other situation is when the object is completely submerged into the liquid. In case it is floating, then in general, we can say that the density of the fluid is greater than the density of the object. And this is a very important formula that it follows, that the volume of the object over the volume of the fluid displaced is equal to the density of the fluid over the density of the object. But in case if it has submerged, then the object density is greater than the fluid density, which means that the force, buoyant force, FB is buoyant force, over the force of the gravity of the object, which is mg, is same as the density of the fluid over the density of the object. Guys, these two formulas are really helpful and are really important. The next is the equation of continuity. The equation of continuity just says that the area multiplied with volume for a liquid at one point is same as the area multiplied with volume over in the other point. So this is A1, this is A2, this is V1, this is V2. So this relationship will hold. This term is very important. Area multiplied by velocity is called volume flow rate, while density multiplied with area multiplied with volume is called mass flow rate. Remember, these terminologies are really, really important. The last one is the Bernoulli. Bernoulli works on conservation of energy per unit volume. It says that the pressure at a particular point multiplied with the half rho v square, where v is the velocity and rho is the density, times rho gh, where h is the height from the reference, is always constant. It means that the energy is conserved per unit volume. And one last statement that is very helpful is if you have less area, this implies you have more velocity. And if you have more velocity, I'm talking about fluid mechanics here, you have less pressure. This is very important. Sometimes there is direct question from this information. Right, guys, that's all what we have in this video. If you liked it, please share it and please subscribe. And if you need tutoring, private tutoring, contact me on the email. Thank you very much.